I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to discuss one more phenomena exhibited by light, that is diffraction. So we are going to study in detail what is diffraction and how it can be observed in day-to-day life and how many types of diffraction we have and why we'll get such diffraction pattern. And then next we are going to discuss diffraction that is occurring at different slits. It can be a single slit, it can be a double slit, or it can be a number of slits. So how it is going to produce different diffraction pattern. So first we are going to discuss about this phenomena of diffraction. Now what is diffraction? So here in our previous videos we were discussing about interference. So what is interference? There we said that when light waves are superimposing on each other, so what we'll observe that depending upon, like in the area of superposition, there will be modification of intensity. So resultant wave, it will have modified intensity. So it can be bright or it can be dark. Then what is diffraction? Diffraction will also give us bright and dark. But in case of interference, we are getting alternate bright and dark fringes, and all bright fringes, they are of same width. And when I say dark fringe, in interference, I'm talking about zero intensity. But whereas in diffraction also we have superposition. Here also we will talk about superposition of waves. And in this case, because of superposition of waves, here also we'll get alternate bright and dark fringes. But you will observe that all bright fringes, they are not of same intensity. Bright fringes, they are of different intensities. So as order increases, intensity of bright fringe is going to decrease, and here dark fringe is not completely zero. It is not of zero intensity. And whereas in case of, we have seen that in case of interference, superposition, it is taking place between the wavefronts that are coming from two virtual coherent sources. Whereas in case of diffraction, here also superposition takes place. But here superposition takes place between the secondary waves which are originating from different points of the same wavefront. That is a very important point we have to understand. So in interference, what is happening? See, in interference and diffraction, both superposition is taking place. But we have seen in Young's double slit experiment, their superposition is taking place between the wavefronts that are coming from two virtual coherent sources, two separate coherent sources. We are dividing the wavefront from the single source. But in this case, what I am doing, I am taking single wavefront, and from that single wavefront, actually it is called as primary wavefront. From different points of primary wavefront, we'll have secondary waves coming out, and because of superposition of these secondary waves traveling in different directions, we'll have diffraction. And in interference, alternate bright and dark fringes. Even in diffraction also alternate bright and dark fringes. But what is the difference here? They all bright fringes, they are of same intensity. When I say dark fringe, we will say that zero intensity. But in case of diffraction, all bright fringes, they are not of same intensity. So intensity of bright fringe keeps on decreasing as order increases. And here dark fringe is not of zero intensity. So to move further, actually how we are going to define diffraction? Actually, diffraction will define it as bending of light around the corners of an obstacle. So what is diffraction? Diffraction is defined as bending of light around the corners of obstacle. If you keep one obstacle in the path of light. Here, if I take here, in this case, this is our light, and what I have kept a slit in the path of light. Or you can also keep one obstacle in the path of light. Then what happens here is, of course, if there is no slit, light, it will be traveling parallelly in this direction. Suppose if there is no slit, then what happens to light? Light, it will be going parallelly in this direction. But because we have kept one slit in the path of the light, also you can keep one obstacle in the path of light. Suppose this is your screen. So if you keep one obstacle in the path of light, then what you will observe here is, and one more thing, what we have to understand here is, that obstacle width or size of that obstacle, it should be comparable with wavelength of light. So this is very, very important point for diffraction. Suppose if E is the width of this slit or E is the width of this obstacle. Now E should be comparable with wavelength of light falling on it. If this is our light, if lambda is the wavelength of that light, if size of the obstacle is comparable with wavelength of light, then what happens? Diffraction takes place. What do you mean by diffraction? So what you will observe here is, in this case, so when this light is going through this, so we'll consider two cases. So if you see here, what you'll observe here is, first I have kept one obstacle in the path of light. So this is our screen. Okay. And then this is our primary wavefront that is falling on this obstacle. This is our primary wavefront which is falling on this obstacle. And here you will observe that these are different points. These are the different points on the primary wavefront. And what you will observe here is, from this primary wavefront, you will have secondary waves coming out of this obstacle. So these are our secondary waves. These are called as secondary waves. So if you see this figure carefully, this is my primary wavefront. These are the different points on the primary wavefront, and from each point it will act as second source of disturbance or second source of wave. These waves that are coming, these are called as secondary wavelengths. And envelope all these secondary waves, it will give rise to new wavefront, and that wavefront it is called as secondary wavefront. So I think you have heard about primary wavefront and secondary wavefront. So this is our primary wavefront, whereas this is our secondary wavefront. So what happens once this is your source light, and in this case what I have kept obstacle in the path of light. So if I keep obstacle in the path of light, what you will observe here is, because here actually you should have geometrical shadow. You should have geometrical shadow here. Okay. And whereas here you should have light. Here we should get light. So here spreading of secondary waves takes place. So what you will observe here is, even in the region of geometrical shadow, you will have secondary waves entering. So here there is spreading of light in the geometrical shadow region also. And that why there is spreading of light? Because of these secondary waves which are coming from different points of the wavefront. These secondary waves, they will be spreading in all possible direction. That spreading of light is nothing but our diffraction. What happens? Suppose if I keep slit in the path of the light. Suppose this is my source. I have kept one slit here. So here, what you will observe, here also geometrical shadow you will have. Here also I will have shadow, and here you have brightness. Now again I have my primary wavefront. From each and every point of wavefront, I have secondary waves going in this direction, and they'll be spreading. And of course, you will have here brightness, and you'll observe that secondary waves going even in the shadow. So here light is spreading even in the geometrical shadow region. This is in case of the slit. Here this is in case of the obstacle. So in both the cases, you will observe that secondary waves which are coming from each and every point of primary wavefront, they are going to spread in all direction, and the spreading of secondary waves is nothing but a diffraction. What is the important condition for diffraction to occur? Size of the obstacle must be comparable with wavelength of light. So now this theory of secondary waves and primary wavefront, it was given by Huygens wave theory. So what is Huygens wave theory? According to Huygens wave theory, every point on the primary wavefront, it will act as secondary source of disturbance. And this secondary waves which are originated from these points, they'll spread in different directions and they'll form one more wavefront. That wavefront is nothing but secondary wavefront. And because of spreading of these secondary waves, we'll get diffraction phenomena. So this is about this phenomenon of diffraction. Now, before moving further, we should have idea about three types of wavefront. What is wavefront? Wavefront is locus of all the waves which are vibrating in the same phase. So locus of all the waves which are vibrating in the same phase will give rise to wavefront. And depending upon the shape of the wavefront, here we were discussing about three types. One is spherical, other one is cylindrical, and third one is plane wavefront. And when you will get spherical and then cylindrical and then next plane wavefront. Now, if you see in first case, I have taken a point source. What do you mean by point source? You can imagine bulb. So bulb, it can act as a point source. If I have bulb here, now what you will observe here is from this point source, you will observe that there are waves that are vibrating in all possible directions, and waves which are coming out in all possible directions, they will be vibrating with the same phase. And if I take locus of all those waves vibrating with the same phase, I'll end up with having spherical wavefront. So what is the shape of the wavefront? Spherical wavefront. So we can see here this formation of the spherical wavefront. So locus of the waves, and from where these waves are coming from the different points of the point source, and all these waves, they should be vibrating with the same phase. If I take locus, then I end up having spherical wavefront. Then how to get cylindrical wavefront? For cylindrical wavefront, what type of source I'll be using? I'll be making use of extended source or line source. So you can take your bulb, tube light. You can take tube light. Now tube light, it can act as extended source. Suppose if you are in the lab, mercury bulb, it will act as point source. Whereas our sodium vapor lamp, it can act as extended source. Now if I have extended source, then from each and every point of this extended source, again I have waves coming out like this. And these waves vibrating in the same phase, if I take their locus, then I end up having cylindrical wavefront. So this is how we'll get cylindrical wavefront. Cylindrical wavefront will be formed when we are taking extended source. Now, coming to third type. Third type of wavefront is plane wavefront. So in case of plane wavefront, what I am going to do here is, you can keep either your point source or extended source at infinite distance. So your source is at infinity. So if you keep your point source or extended source at infinite distance, then if it is a point source, obviously we'll get spherical wavefront. If it is extended source, then we'll get a cylindrical wavefront. Then because we are keeping our source at infinite distance, then what you will observe here is only part of the wavefront. So in this case, part of the wavefront in limited region, that is nothing but our plane wavefront. So a portion of either spherical or cylindrical wavefront limited in small region is nothing but plane wavefront. And what you have to understand here is, if you take this plane wavefront, what is the direction of propagation of light? Direction of propagation of light is perpendicular to plane. It is perpendicular to plane. So direction of propagation of light is perpendicular to plane wavefront. And how we'll get this plane wavefront? When we have to keep our source at infinite distance, then portion of spherical or cylindrical wavefront limited in a small region will give rise to this plane wavefront. So how we'll denote this plane wavefront? We'll denote it like this. This is our plane wavefront. And what is the direction of propagation of light? It is perpendicular to plane wavefront. So this is the representation for plane wavefront. So now we are familiar with spherical, cylindrical and plane wavefront. And based on what type of wavefront we are using in diffraction phenomena, generally we'll have two types of diffraction. So what are those two types of diffraction? Fresnel diffraction and Fraunhofer diffraction. Now, as I told you, based on source, what type of source you are taking, what type of wavefront you are considering for diffraction, and where you are keeping your source as well as screen. So based on all these factors, we have two types of diffraction. One is Fresnel and second one is Fraunhofer diffraction. Now first we'll discuss about Fresnel diffraction. So in Fresnel diffraction, what type of source we are using? We are using either point source, narrow slit, or it can be the extended source. So we can use either point source, extended source, or illuminated narrow slit. So obviously, because we are making use of point source or extended source, so what type of wavefront we'll be using for diffraction? It has to be either spherical wavefront or cylindrical wavefront. And in this case, what I am going to do, suppose this is my source and suppose I am using my slit as obstacle. Okay, and I have my screen here. This is my screen. Suppose this is our screen and this is my slit, or you can also take it as obstacle in the path of light, and this is our source of light. So in case of Fresnel diffraction, both source and screen, they are kept at finite distance from the obstacle. So your source and screen, they are kept at finite distance from the obstacle that is producing diffraction. Because your source and screen, they are at finite distance, so I don't need any lens. I don't need any lens before source. I don't need any lens before screen. Okay, or I don't need any lens before obstacle or after obstacle in order to focus the rays, because both source and screen are at finite distance from the obstacle. So this is about Fresnel diffraction. And completely opposite to Fresnel diffraction, we have Fraunhofer diffraction. Now here in this case, in Fraunhofer diffraction, usually what type of source I will be using? Extended source. So it can be tube light or sodium vapor lamp. And where I am keeping this source? I am keeping this source at infinite distance. What happens if you keep your point source or extended source at infinite distance? You will observe that your wavefront, suppose you have taken extended source, so what type of wavefront will be produced? Cylindrical wavefront. And this cylindrical wavefront, because it is coming from far distance, it will be limited in a small region. And what type of wavefront will be using? Plane wavefront. So whereas in Fresnel, it can be either spherical or cylindrical, whereas in Fraunhofer, it's a plane wavefront. And here if you take both source and screen, they are kept at finite distances. But whereas in Fraunhofer, your both screen as well as source, they are kept at infinite distance from the obstacle. Now your source, it is at infinite distance. So in order to make that wavefront coming from that source fall on your obstacle, obviously you have to make use of lens. And after the obstacle, whatever diffraction phenomena you are getting, in order to focus all those diffracted waves onto the screen, again I need one lens before the screen. So I need converging lens in order to focus the parallel rays. Why? Because our source and screen, they are kept at infinite distance from the obstacle. So because of these differences, we have two types of diffraction. What are those two types of diffraction? Fresnel and Fraunhofer diffraction. Now, compared to Fresnel, I think it is very easy to understand the concept of Fraunhofer diffraction. Next, we are going to discuss about Fraunhofer diffraction at single slit. So what is our Fraunhofer diffraction at single slit? So for that, in this case, I have taken a single slit. So, if you consider here, this is our single slit. So, I have taken a slit AB. It's a narrow slit. And this slit, what is the width of the slit? It is given by E. E is the width of narrow slit. I have taken a slit. And I am trying to see, because of Fraunhofer diffraction from this single slit, what type of pattern will be recorded on the screen. Now coming to experimental setup, because we are talking about Fraunhofer diffraction, what type of wavefront we'll be using? We'll be using plane wavefront. So this W dash will be our plane wavefront. And how we'll get this plane wavefront? We are keeping our source at infinite distance. So this is our plane wavefront. Okay. And I told you that in case of plane wavefront, what is the direction of propagation of light? Direction of propagation of light is perpendicular to plane wavefront. Now, this plane wavefront, it is made to fall on AB. What is our AB? AB is our narrow slit. So AB is our narrow slit whose width is given by E and value of E is very, very small. Okay, and then we have our SS dash. SS dash is our screen, and we know that in Fraunhofer diffraction, screen is also kept at infinite distance. So in order to make whatever secondary waves that are getting diffracted from the slit fall on the screen, I have to make use of this converging lens L. So this is our experimental setup. So what we have here, first we have plane wavefront. So for that we have to keep our source at infinite distance, and the plane wavefront, it is made to fall on single slit AB whose width is E and E is very small. And then whatever diffraction or whatever spreading of light waves is taking place after the slit, in order to record them on the screen, not to focus them on the screen, we are making use of the convex lens L, and we have this screen which is kept in the focal plane of the lens. So SS dash is our screen. Okay, now when this wavelength, and of course this plane wavefront, it has got wavelength lambda, so it's a monochromatic light. It's a wavefront of monochromatic light of wavelength lambda. So what happens when this plane wavefront falls on the slit AB? So as according to our Huygens wave theory of light, Huygens-Fresnel wave theory of light, once this wavefront falls here, then you will have secondary waves spreading in all possible directions. So from this primary wavefront, once it falls on this slit, and if slit width is comparable with wavelength of light, diffraction takes place. So after the slit, you will have secondary waves spreading in all possible directions. So we have secondary waves spreading in all possible directions. Now for simplicity's sake, I am considering two types of secondary waves. One type of secondary waves, as you can see, which are denoted by solid line. And can I say that these secondary waves are traveling exactly normal to the slit, or where theta is equal to 0. First, I am considering set of secondary waves which are traveling exactly normal to the slit. So what do you mean by normal to the slit? Theta is equal to 0. Using this converging lens L, I am focusing all these secondary waves at one particular point on the screen. And what is that point I am calling? That is nothing but P0. And actually this P0 will be the center of the screen. So what is the P0? P0 is the point where all the secondary waves which are traveling normal to the slit are focused. Now, tell me whether P0 will give rise to bright fringe or P0 will be a dark fringe. So for that we should know path difference. As you know that path traversed by all these secondary waves which are traveling normal to the slit, their path difference is 0 because they are traveling straight. So path difference is 0, and if path difference is 0, this is the condition for bright fringe. That's why your central point P0, it will be a bright image. So it's a central bright image. So your point P0, which is the locus of secondary waves traveling normal to the slit, will give rise to central bright image because path difference between these secondary waves is 0. Next, I am considering another set of secondary waves which are making angle theta with the normal direction. So all these are which are shown by dotted lines. If you see all these rays shown by dotted lines, what are these these dotted lines? They represent secondary waves which are making angle theta with the normal direction, and I am making all these secondary waves focus at the point P1. So I've selected one more point P1. How will I get this point P1? This is because of all those secondary waves which are making angle theta with the normal condition. Now I should try to get when P1 will be bright and when P1 will be dark. In order to know when P1 will be bright or when P1 will be dark, my next step is to find path difference between these secondary waves. Suppose this is one secondary wave coming from the point A of the single slit. Then this is another wave which is coming from the point B of the slit. If I am able to know what is the path difference between these two waves which are making angle theta, okay, and which are coming from points A and B of the single slit, then I will be able to get when P1 will be bright and when P1 will be dark. And in order to find path difference, obviously what is our next step? We have to draw perpendicular. So what I have done, suppose if this point I am considering it as P, this point as Q, and this point as R. What I have done, I have drawn a perpendicular from A on BR, and what is that perpendicular? AD is our perpendicular. So perpendicular AD is drawn on BR. So what you will observe here is, after these points A and D, from point A on AP and from point D on BR, their paths will be same. So what is the extra path traveled by BR compared to AP? That extra path will be this path, which is given as BD. So BD is our path difference. So in order to find this path difference, and what is this angle, you will observe that this angle is also theta. So this particular angle is also theta. So here, as you can see here, this is B and this is our path difference between AR. So path difference between secondary waves. Okay. So what are those secondary waves? AP and BR, which are making angle theta. So it is given by delta. So for that I have to take triangle ABD. So this ABD, if I take triangle ABD, so if you see here, if I take triangle ABD, so in this case, if I take sine theta is opposite side, which is BD. So here path difference is our BD. So BD by hypotenuse. What is our hypotenuse? Hypotenuse is AB. Okay. So this, but we know that AB is width of the slit, which is E. So our path difference BD is nothing but E sine theta. So what is our path difference? It comes out to be E sine theta. So this is the path difference between the secondary waves from points A and B of this slit, which are making angle theta with the normal direction. So we got path difference, and once we know path difference, it will be simple for us to find conditions for bright and dark fringes at the point P1. So this is all we have done. So we have taken 2 points, point P0 because of secondary waves making, which are exactly normal to the slit. Then we have point P1 because of secondary waves which are making angle theta with the normal direction, and the path difference, it came out to be E sine theta. And we know that once we know path difference, we can find phase difference. And what is the relation? Phase difference is 2 pi by lambda times the path difference, and the path difference is 2 pi by lambda E sine theta. And what is this 2 pi by lambda? This is the total phase. This is the total phase between waves from points A and B of slit. So from points A and B of slit. So we got path difference, also we got phase difference. Now in order to get conditions for P1 to be bright and dark, now I'm making one assumption. Let us suppose that width of the slit is divided into n equal parts, and amplitude of wave from each part, let it be equal to A. So here what I'm doing, see here, this is our slit. This is our slit. And this is the point A. Okay. And this is the point B. Now I am assuming that, let us suppose that the slit, it is divided into how many slits? N slits. So here you will have so many number of slits. I am dividing this AB into total how many number of slits? N number of slits. Okay. And from each slit, I will have one secondary wave coming out. And what is the amplitude of this secondary wave? Amplitude, it is given as A. So like that, you will have total how many number of waves? I will have n number of waves. And what is the amplitude of these waves? This amplitude of the waves is given by A. And coming to phase, what is the total phase between waves that are coming from point A and B? So it is given by 2 pi by lambda E sine theta. But now I want to find what is the phase between the two adjacent waves, or two waves that are coming from two adjacent parts. The phase difference between any two successive waves from these parts. What I have to do? I have to take 1 by nth time the total phase. But what is our total phase? 1 by n into 2 pi by lambda E sine theta. Let us say that This particular total phase is D. Okay. Now, we are taking help of method of vector addition of amplitudes. And according to this method of vector addition of amplitudes, if we have n waves, n number of waves, and each wave it has got amplitude A, and what is the phase between two successive waves? If T is the phase between two successive waves, then according to the principle, according to this method of vector addition of amplitudes, how can we get resultant amplitude because of n number of waves having amplitude A, each wave having amplitude A and phase difference between two successive waves is D. Then resultant wave, that formula is given by A sine nd by 2 by sine d by 2. This is the resultant amplitude of wave because of n number of waves having amplitude A. And what is the phase difference between two successive waves? It is given by T. So, I'm going to take help of this formula. Now, in this formula, of course, A is there. Then, I'm going to substitute. What is our D? D is the phase difference between two successive waves. And how it is given? It is given as 1 by n 2 pi by lambda t sine theta. So, D is nothing but 1 by n into 2 pi by lambda into e sine theta. If I substitute here, then what you will observe here is, I'll end up having this particular formula. So, pi sine theta by lambda, pi sine theta by n lambda. So, what you will observe here is, I'm introducing one factor alpha, and this alpha I'm calling it as pi by lambda So, pi by lambda e sine theta. So, I'm calling this alpha as pi by lambda e sine theta. So, if I substitute in this particular expression, my resultant amplitude, it gets simplified as a sine alpha by sine alpha by n. And we know that alpha by n, it's a very small value. So, for simplicity's sake, here what I have done, sine alpha by n, approximately I'm taking it to be equal to alpha by n. We know that if angle is very, very small, sine theta is approximately taken to be equal to theta. So, now this Na sine alpha by alpha will get Na is A. If I take this n times the amplitude of each wave, if I consider to be A amplitude, then what is my resultant amplitude? Resultant amplitude, it is given as A sine alpha by alpha. And once we know the resultant amplitude, how we can get resultant intensity? Resultant intensity is nothing but square of resultant amplitude. So, this is the expression for intensity because of intensity at the point P1. And what is our point P1? It is the locus of the secondary waves which are making angle theta with the normal direction. Now, we'll see when I will be maxima and when I will be minima. So, this is very important condition. So, using this condition, we are going to get conditions for principal maxima and minima. First, I am taking condition for principal maxima. Now, I got expression for resultant amplitude as R is equal to A sine alpha by alpha. So, I got this expression. So, here, what you will observe here is, now, if I take A by alpha outside, how can I write this sine alpha? We know expansion of sine alpha is alpha minus alpha cube by 3 factorial plus alpha to the power of 5 by 5 factorial and so on. This is our expansion. And if I take this alpha, if I cancel this outside alpha, I end up having R as A into 1 minus alpha square by 3 factorial plus alpha to the power of 4 by 5 factorial and so on. This is what we got here. So, here in case of this, I'll have 1. This is our 1. So, 1 minus alpha square by 3 factorial and so on. And here, what you will observe, when this resultant amplitude will be maximum, as you can see here, we have powers of alpha. So here powers of alpha is very small. So if I can neglect all these powers of alpha, then I can have maximum amplitude. So I can say that intensity will be maximum or value of R will be maximum if I consider alpha to be 0. This is the condition in order to get maximum amplitude. And we know that what is alpha? Alpha is pi by lambda E sin theta. And from this I end up having sin theta is equal to 0. And this is nothing but theta is equal to 0. What do we mean by theta is equal to 0? So theta is equal to 0. I'm talking about this point P naught. Point P naught, secondary waves which are traveling exactly normal to slit or where T naught is equal to 0. So here you will have maximum intensity. And what is the maximum intensity? Maximum amplitude, it is given by A, and maximum intensity, it is given by A square. And this maximum intensity at the center of the screen, which is point P naught, it is formed by secondary waves which are traveling exactly normal to the slit, and this is known as principal maximum. Then we'll talk about minimum intensities, minimas. Now again I have this expression for intensity. What is the expression for intensity? Intensity is A square sine alpha by alpha whole square, and minimum is 0. Intensity will be 0 if I consider sine alpha to be 0. If I put sine alpha 0, then my intensity will become 0. Then I can get minimum intensity. I cannot take A to be 0 because it is n times the amplitude of each wave. And for which values of alpha, sine alpha will be 0 if alpha is equal to plus or minus m pi. Now what is m? So here m, it starts from 1, 2, 3 and so on. I cannot take m to be 0. What happens if I take m to be 0? Then my alpha will become 0, and alpha is equal to 0 is the condition for principal maxima. So these are the values of alpha for which I get minima. So your point P1 will be minimum if alpha value is equal to this, or what is alpha? Alpha is given by pi by lambda E sin theta, or if your part difference is equal to plus or minus m lambda. What is plus or minus m lambda? So plus or minus lambda, plus or minus 2 lambda, plus or minus 3 lambda, and so on. So if this condition is satisfied, then we'll get minimum intensity. And because here plus or minus is there, it means that first at the center P naught I'll get maximum intensity. On either side of principal maxima I'll have minimas. So this is the condition. M is equal to 0, sin theta is equal to 0. So this is for principal maxima, and we have points of minimum intensity on either side of principal maxima. Now we got the condition for principal maximum. What is principal maximum? Where you have maximum brightness, where intensity is more, and how that intensity is given, it is given by A square. And then we have minimas at position plus or minus m pi. Now apart from principal maxima, you will have secondary maximas. What are secondary maximas? These are bright intensities, but their intensities will be less than that central maxima intensity. And we know that in order to get secondary maxima, if I take mathematical expression, if you have any function to be maximum, so here what you will observe here is you have first derivative of that function, it will be equal to 0. So that's why di by d alpha, if I differentiate it with respect to alpha, it should come out to be 0. I know what is I. I is A square sin alpha by alpha whole square. So if I differentiate it, so A square if I take out, then I have, so sin alpha by alpha whole square. So it will give rise to 2 sin alpha by alpha. Now sin alpha by alpha, if I take sin alpha into 1 by alpha as 2 terms. So first sin alpha gives rise to cos alpha. Okay, cos alpha into 1 by alpha. So by 1 by alpha, and then sin alpha will be as it is, and 1 by alpha it will give rise to minus 1 by alpha square. And if I simplify, I'll get this. I end up having this. Okay. So now what we can see here is there are many parameters equal to 0. Now first I'm talking about this amplitude A. A cannot be equal to 0. Sin alpha also cannot be 0 because sin alpha is equal to 0 is the condition for minimum. And alpha also cannot be 0 because this is the condition for principal maximum. So what I can do, I have to take this particular equation to be 0 for this whole term to be 0. So that's why alpha, cos alpha minus sin alpha is 0, because as I told you, this gives positions of minima. And if I take this condition, I end up having alpha is equal to tan alpha. Still, I'm not able to get those values of alpha, for which I'll get secondary maxima. What are secondary maximas? These are maximas, of course, whose intensity will be less than the principal maxima, and where they are present between the two minimas. Now, if you see here, in order to get values of alpha, what I'm going to do, I'm going to plot two curves. One curve is y is equal to alpha, another curve is y is equal to tan alpha. So these two curves I'm going to plot in the same graph. And when after plotting, when these two curves, they'll meet at certain points, and those points will give points of intersection of this curve alpha is equal to tan alpha. So that we are trying to do here. Now, on x-axis, I have taken alpha. Okay, so what are the values of alpha? So alpha, it can be pi or pi by 2, then pi, 3 pi by 2, and so on I have taken. So now, because first I am going to take y is equal to alpha. So this is my y is equal to alpha curve. So y is equal to alpha, we know that it's a straight line equation which is passing through the origin. Then one more graph, y is equal to alpha, it will give us straight line passing through the origin. And what are the values of alpha I'm taking on the x-axis? They are multiples of pi. Now I have to plot y is equal to tan alpha, and already we know that. So here y is equal to tan alpha. If I substitute alpha is equal to 0, then tan 0 is 0. Okay. Then next I'll take tan 30 degrees, then tan 60 degrees. Then if I go to tan 90 degrees, so here what you will observe here is a tan pi by 2. So it goes to infinity. Okay. So there is discontinuity. Actually, it's a discontinuous curve. You'll have discontinuous at which positions? At positions plus or minus n pi by 2 or m pi by 2. So at alpha is equal to plus or minus m pi by 2, you will have discontinuities at tan curve, because at these values, what happens to tan value? It goes to infinity. Okay. Now, if I get such curves, okay, periodic curves I'll get. Now, when I consider one curve y is equal to alpha, another curve y is equal to tan alpha, and now if I consider where they are meeting at these points. So these are the points where these two curves are meeting, not this one. So these are the points where these two curves are meeting. Okay. But now if you take, this is 3 pi by 2. Then this one, this particular point value, alpha is equal to, actually, it is 1.43 pi, or I can take it to be approximately 1.5 pi, or it is approximately 3 pi by 2. Similarly, if I take this point, so alpha is equal to 2.46 pi, which is approximately 2.5 pi, and which is approximately 5 pi by 2. Similarly, same is the case. So what are the points of intersections of these two curves? Points of intersections of these two curves will be not 0. Points of intersections will be alpha is equal to plus or minus. Actually, alpha is equal to plus or minus 1.43 pi, plus or minus 2.46 pi, and so on. It means that alpha is equal to plus or minus 3 pi by 2, plus or minus. These are the points of intersection of those two curves. And if I substitute, see what is the formula for I got it as a square sine alpha by alpha whole square. Now, if I substitute alpha to be 0, then my maximum intensity, which is at the point P0 on the screen, it is a square. And if I substitute alpha is equal to 3 pi by 2, I end up having my intensity to be a square by 22. And if I substitute alpha to be 5 pi by 2 in this expression for intensity, I end up having intensity to be a square by 62. What does it indicate? It means that as alpha value is increasing, what is happening to intensity of maxima? Maxima keeps on, its intensity keeps on decreasing. So maximum intensity is at the center, which is principal maxima. And coming to secondary maximas, as alpha value increases, what happens to their intensity? It keeps on decreasing. And where these principal maximas are present, they are present on either sides of the principal maximas in between the minimas. So putting all those points together for principal maximum, minima and secondary maxima, so what type of pattern will be recorded on the screen? So this is our pattern on the screen. So in case of interference, what is the pattern that is recorded on the screen? I have all bright fringes and their intensity is same. And what is that intensity? Intensity is 4a square. But here in this case, at alpha, this is with respect to alpha. At alpha is equal to 0, I have principal maxima whose intensity is maximum. What is that intensity? A square. Followed by minima. Where did I get minima? So I'll get minima at alpha is equal to plus or minus m pi. That is nothing but plus or minus pi, plus or minus 2 pi and so on. So wherever I have pi, 2 pi, 3 pi, minus 2 pi, 3 pi, I have minimas. Then how to get secondary maximas? What we got for secondary maxima? For secondary maxima, alpha is equal to plus or minus 3 pi by 2 plus or minus 5 pi by 2. So here, and what is this intensity? A square by 22. So this intensity is also a square by 22 and this is a square by 62 and this is a square by 62. So intensity keeps on decreasing for secondary maxima. So putting, this is because of interference and this is because of diffraction from single slit. So what type of pattern is recorded? I have central maxima at alpha is equal to 0, minimas at alpha is equal to plus or minus m pi, and secondary maximas of decreasing intensity at alpha is equal to plus or minus 2m plus 1. Alpha is equal to plus or minus 2m plus 1 pi by 2. These are for secondary maximas. So I hope you are able to understand about this. So with this, I'll end up my video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.